they will be available today, but since it's Monday classes and so some of the classes will be using rooms in DCC. So he'll be available online. So via WebEx, you can reach out to him if you want to ask him any questions, have some discussions. There is also a tutor that's available through Alec in the Shellnut Gallery in the Union. So he actually took the class with me last fall. So it's definitely another good resource to utilize if you want a little bit more one-on-one interaction. And of course, I'm available to you if you have questions as well. The first homework is going to be due tomorrow night. So make sure if you haven't, definitely take a look at that. It can be a little bit difficult at first getting used to the way Gradescope is, just having the different ways that you can input different solutions. So definitely take a look at that ahead of time. Don't wait till the last minute to do that submission. All right, so last time we left off with this idea of different kinds of system properties. And what we found was a really interesting one, and we'll see why in a little bit, is time invariant, linear time invariant systems. So typically, right, it's a lot of words to write, so I'll just refer to them as LTI systems. And so for a lot of the things going forward, we'll be looking specifically at these kind of systems. So what is an LTI system? Well, if I have an input, let's call this X1, and I feed it into a system which I know is an LTI system, and then I get some output, let's call it Y1. If I take another input and pass it through the same LTI system, and I know what that output is, then if it's a linear time invariant system, I can do a linear combination of these inputs, meaning I can scale them and combine them together through addition or subtraction, because you can have a negative multiplier. And I can also time shift these signals. So let's take a look at an example there. We'd say we scale our first input and we time shift it. And I combine this with my second input, which is also scaled and time shifted. Now, if I put this into an LTI system, then what I get is the output. I can take each of these individual components. If I scale this, then due to linearity, I'm going to get a scaled version of the output. Time invariance tells me that if I time shift the input, I get the same time shift in the output. Linearity also tells me that if I combine two signals, then the output is a combination of those individual outputs. So I can also scale and time shift the other output. So let's take a look at an example LTI system. And this will also serve, hopefully, as a quick little review of what you've seen in circuits and also in differential equations. So we're going to take a look at an RC circuit. And we're going to assume that the capacitor has zero initial charge. All right, so zero initial conditions. So I'm going to sketch my RC circuit here. So we have a resistor, we have a capacitor. My current is going to be going through this circuit like that. And if this X of t is my input voltage, I'm going to take my output voltage, Y of t, to be across the capacitor. So to make things a little bit easier, because we're really looking at this more just for the procedure and mathematical purposes. We're just going to say our R and C are both 1. Right, makes things a little bit simpler when we start solving things. All right, so hopefully a little bit of review, the relationship between our different components. I'm going to put these to the side here. All right, so if I say V is the voltage across that component, and then I is going to be the current through that component. Then if I have a resistor, the voltage is the current times the resistance. If I have a capacitor, then we start getting into our differential equations. So we have the derivative of the voltage across the capacitor is equal to 1 over C I. And if I have a inductor, then it's the derivative of the current 1 over L V. So if I go to my specific circuit here, so we have a capacitor. And this capacitor, the voltage across it is Y. So we have dy dt equals 1 over C I. Oh, it just made things simple and said everything is 1. So this is just the same as that current I. And just so we can reference this later, I'm going to call this equation 1. And then I'm also going to do a voltage loop equation. All right, so going around the loop, the voltage here, we have minus x of t, plus the voltage across the resistor is I times R, plus the voltage across the capacitor, the voltage around the loop is 0. And so I'll take this x of t to the other side. So we have x of t is I. I'm going to plug in my R equals 1. And let's call this equation 2. All right, so I want everything in terms of my input and output, which means I need to get rid of this current here. So I'm going to use equation 1. We're going to substitute 1 into 2. And what we're going to get is dy of t dt plus y of t is equal to x of t. All right, so this is an equation that describes this circuit. And we note that we assume there is 0 initial charge across the capacitor, so that means y of 0 equals 0. So a little bit of another aside here. So when we have first order ordinary differential equation with our constant coefficients, right? So just like the form that we have here, right? So it's a first order because we only have a single d dt about d squared, dt squared would be a second order, and so on. And constant coefficient, right? Because we have the coefficients for each of those terms doesn't depend on t. And so if you have something, well, first I'll do a little bit of notation just to make it a little bit cleaner. If you're not familiar, we can use dot notation to denote our derivatives. So my first order ODE with constant coefficients, I would have derivative coefficient on my just y term. And then we have some function of t on the other side, right? So if there's some factor out here, I can always divide it through and lump whatever this is in with that a and in with the g of t. So it's fine that we have it in this form. So if you have something that looks like this, then your solution, y of t, is going to be composed of two parts, a yh and a yp. We refer to this as the homogeneous part and this as the particular. And so your homogeneous, how you get that is you plug in your homogeneous solution and you set that g of t equal to 0. Yes. In this one? We are substituting r equals 1. Yep. Yep, we're kind of lazy with it, so we just make everything 1. Right, so if I have this form, then the solution to this, yh of t, we're going to have some coefficient c, e to the minus at. That's going to be your homogeneous part. And then your particular part is going to be of similar form to g of t. Right, so if it's a constant, then your particular solution is likely to be a constant. If it's a sinusoid, likely to be a sinusoid. So with that little bit of an aside, if we go back to our circuit that we had, all right, so we had dy of t, et, plus y of t equals x of t. And so now we need some particular input. Let's say we're interested in the step response of this circuit. So the step response would be when our input, x of t, is the step signal, u of t. Right, so in that case, what we would get if we use the solution method here, that response y step of t, we're going to get 1 minus e to the minus t, u of t. Right, and so I can verify this by looking at my equation, and this will be a little bit of review of differentiation. Right, so if I want to take the derivative of this, then I need to use the product rule to do that. So what I do is I take the derivative of the first part. The derivative of a constant is 0. Derivative of exponential, I take this coefficient down. Minus times minus is a positive. Be it e to the minus t. And the second part stays the same. Plus the first part times the derivative of the second part. So last class, we said that with the step signal, right, we can't really do the differentiation in the way that we're used to with calculus, but we ended up defining this special little signal, this delta of t, which is our derivative of our step signal. Right, so let's see if I plug these in back into my expression, if it actually is equal. So our derivative plus the signal, we substitute in our solutions here. So we have e to the minus t u of t plus 1 minus e to the minus t delta t, and then our y step, 1 minus e to the minus t u of t. So if we're looking at this, we can see this term and that term are going to cancel each other out. We have plus minus e to the minus t u of t. And then for this part, right, so we know that delta of t, by our definition, is 1 when t equals 0, and 0 everywhere else. So what that means is that this delta is going to cancel out all of the values for this signal everywhere except where t equals 0, right? So the only point that actually matters to us is what the value of this signal is at t equals 0. And so if I substitute in t equals 0 here, at 1 e to 0, e to the 0 is 1, we have 1 minus 1 is 0. Right, so it turns out that when I do this multiplication of these two signals, that it turns out to be identically 0. Right, because this is 0 everywhere except t equals 0. This is 0 where t does equal 0. That means it's 0 for all t. So these two canceled out. This turns out to be 0. And so we are indeed left with our original input, u of t. All right, so if I'm interested in, say, plotting this step response, that gives me an idea of how my circuit is behaving. So if I have something that's of the form a plus b e to the minus k t, all right, we're going to assume k greater than 0, so we actually have a decaying exponential in that second term. So a few key points that we can recognize is that when t is equal to 0, we have a plus b e to the 0, right? It's just a plus b. So we always know where that 0 point is. And as t goes to infinity, then we have a plus b e to the minus infinity. Right? E to the minus infinity goes to 0. And so this term goes to 0, and we're left with a. So as we go to infinity, we're going to be converging to that a value. So since we're given our y step of t that we found was 1 minus e to the minus t u of t. All right, so at t equals 0, our a is 1, our b is minus 1. So at t equals 0, we're going to be at 0. And we're going to converge towards 1. And since it's a step signal, this is 0 for t less than 0, 1 for t greater than or equal to 0. So we just have 1 multiplying the signal, so we can sketch this. And what we get is something that approaches 1. So the real power of these LTI systems is that, right, solving these ODEs is probably a little bit annoying, right, when we're doing something like this. But for this case, it wasn't too bad. We had just a simple u of t as the input. But now what if I want to know what is the response to the signal x of t, which let's say we're 0, and then jump up to 1. jump down to -1, and then back up to 0. And this is going to occur at 1, 2, this height is 1, and this height is -1. Okay. So if we actually wanted to solve the ODE with this input, right, it's going to be a lot harder for us to do that. But we can use our knowledge of LTI system to avoid having to redo that differential equation. Why that is because if we look at x of t, we can recognize that x of t looks like a u of t, as if I indicate each of these here, right? That would be our u of t. Subtract from that a height 2 step, which is shifted by 1. So this would correspond to a height 2 step signal. So it's going to cancel out that +1, add another -1. And then it's going to be plus an additional signal, which is going to cancel out that -1 remainder that we have. So we're going to add to this another u of t. Like so. Right, so if you add those 3 different colored signals together, then you would get the pink, which is our x of t. And so now as we look at this, we can see that this x of t is actually a linear combination and time-shifted version of this x of t that we already solved for. So what that means is that since I already have an output for that step signal, then the output for this signal, output of u of t, I already derived that. This one is scaled, which we know that LTI system, we're going to get a scaled version. It's still a step signal input, so we're going to get a step response output. And it's going to have the same time shift because it's a time invariant system. And similarly here, we have no scale factor. It's a step input with a time shift. So now, what I need to do is just plug in my t's into what I had for my y step. So my y step was 1 minus e to the minus t u of t. Now we have a scale factor, and everywhere that I have a t in my y step, I'm substituting t minus 1. So we have 1 minus e minus t plus 1, u t minus 1, plus 1 minus e to the minus t plus 2, u t minus 2. Right? So no additional solving of the ODE is necessary. We did it once, and then we can use the properties of our system to avoid having to do that solution again. And so if I actually wanted to sketch this signal, probably the easiest way is to first write this in bracket notation. So when t is less than 0, then this is 0, 0, 0. So everything is 0 when t is less than 0. When t crosses 0, this becomes 1. These two still stay 0 until we get to t equals 1 and t equals 2 for each of these cases. So we have just this 1 minus e to the minus t when we're between 0 and 1. And then once we cross 1, then this ut minus 1 becomes 1. So we have 1 minus e to the minus t minus 2 plus 2e to the minus t plus 1. Do a little bit of simplification. And this is true between 1 and 2. And then once we cross t equals 2, then this also becomes 1. So if we do the same algebra, so we're adding all of these coefficients here, doing some simplification. And this is true for t greater than 2. All right, so definitely would have been a very weird solution to try and get just solving the ODE directly. If you're interested, this is not going to be maybe the best sketch. Definitely not my forte. But kind of give you a rough idea of what this would look like. So we're going to have t equals 0, 5t equals 0 for t less than 0. And then we go and move towards 1. How we don't actually hit it up to t equals 1. And then we start having this decay between 1 and 2, where we're going to approach minus 1. And then we're going to have this term here, where we're going to be going towards a 0. So, like I said, it's kind of a weird solution that you might not have expected, just trying to look at this x of t that we have here and trying to solve the ODE. But we were able to do a simpler ODE and then use our properties of LTI systems to figure out what the response was to a more complicated input signal. And we'll be utilizing that idea quite a bit as we go forward in the class to essentially trying to avoid a lot of complicated math by using some properties and relationships. All right, so it turns out that with a lot of different systems, so there's actually a variety of systems that we can describe by these linear constant coefficient differential equations. All right, so continuous time system, we're going to have these differential equations. In the discrete time case, there's an equivalent form, which is linear constant coefficient what we call difference equations instead of differential equations. And so essentially what these difference or differential equations, depending if it's continuous or discrete time, give us is an input-output relationship for our system. And if we want a particular response, right, what's the output, we actually have to plug in an input and solve that either differential or difference equation, but it gives us the general relationship between that input and output. So our linear constant coefficient differential equations, so those are going to be of the form, so maybe something like what we saw before. Where we would say x is our input, y is our output, and then a is just some constant that describes that relationship. And you can extend this to higher order as well. So you can have a linear combination of different order differences here, differentials. All right, so you could have a dt, d2, dt2, d5, however many derivatives that you want to take. You can do a linear combination of all of these derivatives of the output. And you can also do the same thing with the input as well. Right, so we can also have derivatives of our input signal. And this is still a linear constant coefficient differential equation. And so if you actually want the output, you plug in your input, solve this ODE to get your actual output. And one thing that we'll note is typically for this class, we're going to assume 0 initial conditions. All right, so you can solve for those more complicated ones as well. For the purposes of this class, we'll just assume 0 initial conditions, and we'll find pretty quick that we can actually use some of our transforms to convert these differential equations into algebraic equations. So something to look forward to as you suffer a little bit with some of these differential equations. And so the equivalent, that linear constant coefficient difference equation, what those are going to look like is you're going to have a summation of linear combinations of delayed versions of the output, so current and past outputs, and those are going to be related to a linear combination of current and past inputs. So same kind of idea, that if you're solving something like this, you're also going to have this kind of concept of a homogeneous solution where you take and assume the input is 0, solve for having just your outputs equal to 0, and then once you get this solution, then you can find the particular solution. All right, so it's actually a similar kind of idea for solving these discrete time cases. Right? We're not really going to look into that part of it because it turns out that there's actually a little bit easier way of solving these kind of equations. If we take a look, what we notice is that we can rewrite this equation. So let's take first our k equals 0. So in k equals 0, we have our yn, which is typically what we're actually looking for. What's the output at this current time? So I'm going to isolate that yn. When k equals 0, it has a multiplier a0. So I'm going to bring that to the other side. And I'm going to bring all of the other y terms in that summation also to the other side. So we have all of our x terms minus, I pulled out k equals 0. So I'm left with all of the other terms there. And so what this means is that my yn depends on yn minus 1, n minus 2, right? So on and so forth up to yn minus n. Right, so all past outputs. So what that means is that I can actually solve these difference equations recursively. Right, so I can first find what is y of 0, get that solution, plug in the y of 0 to get my y of 1, and so on and so forth. All right, so that's probably the easiest way to solve these kind of problems. And we'll take a look at an example here of how we can do that. So let's say that for our system, we can describe it by this difference equation, y of n is x of n plus 1/2 y n minus 1. And our initial condition is 0. And so now let's say I want to know what is the output of this system if I have x of n is equal to k delta n, which means it's going to equal k when n equals 0 and 0 over. Okay, so we know then that x of n is 0 for n less than 0. And we were also told that our initial condition was 0. So what we know is that y of n is equal to 0 for n less than 0. So what we start with then is when n is equal to 0, we wonder what is that output y. Well, if we look at our equation here, so when n equals 0, we have x of 0 plus 1/2 y of minus 1. So we know x of 0 is k, and our y of minus 1 is 0 because of that 0 initial condition. So we have k plus 1/2 times 0 is just going to give us k. And so like I said, I can do this recursively. So now I can compute y1, which is x1 plus 1/2 y0. So x is 0 everywhere except n equals 0. So that makes it a little bit nicer doing this. And then we have 1/2. Our y of 0 is k. And I can keep continuing on like this. Okay. I'll do one more case here, so maybe we can start to see what the trend is. And so if I wanted to figure out, in general, what is y of n, all right, so I have xn plus 1/2 y n minus 1. All right, so depending on how your mind works, you might be able to see that we can actually rewrite this. This is like 1/2 to the 0 times k is like 1/2 to the 1. 1/2 squared, 1/2 cubed. All right, so if we continue that trend on, then what we can see is that this is the same as 1/2 to the n times k. Right, so that's a way that we can solve these kind of problems. We can do this as a recursive way. If we want some specific n, then we can just start with y of 0 and propagate that forward. And so if you have a system which is described in this way, so if you have a system with our constant coefficient difference equation, and we have the 0 initial conditions, then that is going to be an LTI system. Right, so the equivalent of what we saw in our continuous time, we have the same idea for this discrete time case. And so what's actually really interesting for LTI systems is that we can also figure out a way to figure out the output to any input. Right, so we said before, if I know the response, say, to u of t, and I know that my input is some linear combination of shifted and scaled versions of u of t, I can figure out the output to that. But it turns out that if you have an LTI system, then the output is characterized by a special characteristic unique to LTI systems, which are referred to as the system's impulse response. So what we're going to find is that for an LTI system, continuous or discrete time case, if you can figure out what is the output to that LTI system, given the input is an impulse, so delta n or delta t, depending continuous or discrete time, that you can figure out the output to any input to that system. So a really powerful relationship. And if we take a look at this, this one that we just did here, right? Essentially, this is like our impulse response. We just need to set this k equal to 0. So for our example, if we set k equals 0, then what we have, and we're actually going to give this output a special indicator, so we're going to use h. So h is going to indicate that that's the impulse response. Is going to be 1/2 to the n u of n. Right, because we know that the output, if n is less than 0, is going to be 0. So that's what this u of n captures. And when n is greater than 0, we have this form. But if we want just the impulse response, then that's when that k equals 1, because then we'd have the input is just that delta n. So this h of n here is our impulse response. So interesting ideas that we have there. And so if you have this impulse response, then what this is going to lead to is the idea of convolution, right? So we'll first look at this for a discrete time case. And next time we'll look at what the extension is for continuous time. And what we'll find is that convolution, which is going to be a way that we can figure out our y given any x, in discrete time, that's going to look like a summation. Right? So if we have an LTI system, and we know if we take an impulse, put it into that LTI system, then the output that we get, we're going to call our H of n our impulse response. So let's see if we have, let's say here, a delta n. We're going to sketch this out. Let's just put a bunch of numbers here, like so. So our impulse is going to be 0 for all n, except where n equals 0, where it's going to have a magnitude of 1. And let's say that I put this into my LTI system, and the response that I get, so let's say I end up getting zeros, then we have a value with magnitude, whatever that h of 0 is, and let's say we also have an h1, an h2, an h3, and then let's say it goes back to 0. So what I know with LTI systems is that if I take my input and I shift it, right? So let's say that instead of delta n going in, I have delta n minus 1. So minus sign, that means I'm shifting it to the right. My impulse now, instead of occurring at 0, is going to occur at 1. Then I know through time invariance that I take my output and I shift it in the same way. Right? So what was at 0 is now going to be at 1. At 1 is now at 2, right? So on and so forth. And I can also use my linearity, the superposition combination of all of these properties to say, let's say if I have a delta n plus a shifted delta, right? So my delta n is going to be 0 everywhere except n equals 0. And my delta n minus 2, the impulse is going to occur at n equals 2. So my overall signal would be the sum of those two. And so if I pass this into my LTI system, I'll do the individual, and then we'll see when we combine them. So the response to delta n we're going to get 0, H0, 1, 2, 3, and then we had all the rest were 0. The response to my shifted input, so we're going to have, these are going to be shifted 2 to the right. So that means that my overall output is going to be the combination of these two individual outputs. And so what I would get, 0 plus 0. Here we have just h of 0, just h of 1. At this point, we have a summation of h0 plus h2, h1 plus h3, and we have an h2 and an h3. All right, so just adding the individual responses together to get the overall response to that signal. And we could do the same thing if we have scaling, right? So if this was, say, 2 delta n, then we just multiply each of these individual outputs by 2. So why we say then that this h of n can tell us the output for any input signal, right? So even if we have something that has more complex, something like this, why can we say that that actually fully characterizes the output? Well, if we look at any discrete time signal, so let's say we have an x of n, which is going to have a bunch of values at different n locations. What I can do is I can write this as a series of scaled shifted impulses. Right, so I get the magnitude from whatever that x of n value is, and then the delta gives us that location on the independent axis. And as I shift my deltas, then I'm shifting those values. And I can have however many I need to capture all of the non-zero values of x of n. Or I can write this in a more compact form by using a summation like so. So what that means is that if I'm looking for the output to this input signal, so my output, y of n, well, these x values here are just numbers, so those are just scale factors. And then I can take what I learned from up here and recognize that if I have delta of n, the response is h of n. And if I shift it in some way, I just get a shifted version of that h of n. So the response to this first part, we have our scale factor. The response from delta of n is h of n. We have a scale factor. And the response gets shifted. And we can do this for however many terms there are. H is the output. And I can write this more compactly. Like so. And so this is what we refer to as the convolution sum. Right? So once we get that h of n, then given any x of n, I can compute what the output y of n is by using this summation. So that's why we say then that the impulse response completely characterizes the system. Why? Because from this impulse response, we can compute our output for any input x. And I will make a note here that the way that we denote convolution and does confuse some students at first. They assume it's multiplication, but what we're going to do is we're going to use an asterisk. So x of n, this asterisk means that we're doing a convolution, not a multiplication. So when you see that asterisk in between two signals, if it's this discrete time case, what this means is this convolution summation. Right. So there is one really powerful property that's associated with convolution, is that if I have two signals, x and h, that I'm convolving, x convolved with h is the same as h convolved with x. Right? So what that means is that if I take, and let's say I have y is x convolution h, then from my definition, we have a summation xk h n minus k. And if I have, instead I do h convolved with x, then I'd switch this around and I'd have hk x n minus k. And so it turns out that my y is equal to my z, and that's true for all n. Because what I can actually do is I can substitute in. So if I say, we'll just call this L be n minus k. So k is equal to n minus L. So k, as that goes to infinity, L is going to go to minus infinity, and vice versa. So if I do this substitution into, say, my y, I would get y. Right, so we start off with our summation here, xk h n minus k. I do this substitution where it's in terms of L instead of K. So we have summation of x n minus L h L. And so we can see that this is the exact same form as what we have here. We just used a different letter. Right? And it turns out that that's just a dummy letter that we use for our summation. So this is indeed the same as z of n. So what's nice about this is that if you're looking at your summation and you say, well, it's actually easier to do the K substitution in one signal versus the other maybe makes the math a little bit simpler. It turns out that you can swap which one you do that substitution in. So it can be either XK or HK, depending on which one you want to use. So there's different ways that we can also solve this summation. So there is a special case where if we have our signals are both finite length. So by finite length, I mean there's only a set number of instances of n for which we have a non-zero value. And it turns out there's a little bit of a shortcut that we can take. So we have a special case where we have both xn and hn have a finite number of impulses, finite number of non-zero values. So let's take, for example, let's say that we have x of n, have a bunch of zeros, and then we have 2, 1, 1, bunch of zeros. Okay, so remember our notation. What that under bar means is that corresponds to n equals 0. And we can increment up on the right side, so this is n equals 1, 2, 3, and so on. N equals -1, -2, and so on. And then let's say our h of n like so. Right, so we only have 3 non-zero values for each of these signals. So if I look at my summation, what I would find is when n is less than 0, what we would have is our y of n is the summation of xk, h, n minus k. But for any n which is less than 0, then what we're going to get is that h of n minus k is equal to 0. And so our y of n is going to be 0 for all of these values. Right, because what's going to happen if we're looking at the way that we sketch these signals, sketching it in terms of this x, what you would have is you'd have a flipped version, and then you'd be shifting it by n. And so all of your n minus k would be 0 for those cases. And we also have a similar case when n is greater than 4. Right? So our x of k we know is 0 when k is less than 0 and when k is greater than 2, because we only have 0, 1, and 2, that x is non-zero values. And our h n minus k for those cases is going to be 0 when our k is between 0 and 2. And so if you sketch each of these signals out, you can also visualize it that way. We'd get y of n equals 0. And then if we look at the in-between cases, okay, so let's say n equals 0, then you would have y of 0. We would use just our non-zero values of x, because we know everywhere that x is 0 is going to cancel that out. We have x, k, h, plug in our n equals 0. And so you'd have all your different values of k. Substitute all those numbers, do some algebra, right? And so you can continue this on and figure out what the values are for each of those n's. Or for signals which are of this form, there's actually a little bit of a shortcut that we can take. What we can do is for finite length signals, what we can do is use what's called the array method. All right, so what this allows us to do is we're going to take and form an array. And you could do either or. For this one, I'm going to put the h's on the top. You could put the h's on the side and the x's up here. Either way, it'd still get you the same result. So you take all of your values of h, starting from the first non-zero value and going till the last non-zero value. Right? So if you had, say, h3 and maybe your h2 was 0, you must still include that 0 that's in the middle. Right? If you just skip over everything that's non-zero, you will get the wrong result because you'll actually be missing some of the terms. And I do the same thing over here, but I take all of my x's. And so these I just put as a reference so I know what's going into the array itself. So this is the array that we're actually interested in. And so what I do is I form each element of the array by taking the column header and the row header and multiplying them together. So I'm going to get all of my x's across the row. And I'm going to get all those h's across that column. So each element of the array is going to be your h times your x. We're going to use whatever, say in this case, that I is the row value and j the column. Right, so you're multiplying each of those to form your array values. And then to get the actual y of n, you're going to add the elements along, I'm going to call these back diagonals, just because for me, I would think that these would be your diagonals. We're going to be looking at the ones angled more like a backslash. So if I rewrite this form here, so your array has to have x0, h0, x1, h0, x2, All right, so for this one, I'm showing a three-link signal. You can extend this to smaller or larger signals as well. All right, so once you have your array form here, then what I'm going to do is I'm going to sum along these back diagonals, and these are going to give me my y of n values. And so the question is, which of these corresponds to n equals 0? Right? Because if we just have a bunch of numbers, but we don't know what n's they correspond to, it doesn't help us very much. So what we do is we look for which diagonal has the multiplication of the two 0 elements. So this one has our x0 and our h0. So that means that this diagonal here corresponds to y0. And then as I move to the right, I'm increasing my value of n. And as I'm moving to the left, I would be decreasing that value of n. And so if we take, for example, looking at y3 here, so that y3 would be x1 h2 plus x2 h1. So it's maybe a little bit confusing at first when it's more abstract, but once we look at a example with numbers, it'll make a little bit more sense. So if we take the example that we were looking at before, so for our example, we had xn, we had, let's say, 2, 1, 1, and we had hn is 1, 2, 3. And so if you use the method that we had before, right, actually going through and computing the summation for each of those n's, what you would get is y of n. We have 0, 2, 5, 9, 5, 3. So now, if I use the array method, what I'm going to do is I'm going to take my h values and use those to label my columns. So we have 1, and I want to make a point of indicating which ones correspond to n equals 0, so I can use that to figure out what my n equals 0 reference is for y. So we have 1, 2, and 3 to label our columns. And I take my x's to label the rows. We have 2, 1, 1. And so each of my elements, I take the column times the row. So we have 2 times 1 is 2. 2 times 2 is 4. 6. We have 1, 2, 3. 1, 2, 3. And I note that this element here is that 0 element that I'm interested in. So I took my x of 0 and my h of 0 and multiplied to get this array element. And so from this array, I can add up my back diagonals. And I know, since this is my reference point, that this is y0. y1, y2, y3, y4. And so now I can see here my y of 0. The only element there is 2. y1, I have 4 and 1. y2, and as we see, as we're comparing to what you get from doing the summation directly, that we get the same result. And all the elements that we don't have are just 0. Okay, so maybe it takes a little bit of getting used to at first, but once you know what the method is, then you can do this a little bit more quickly than actually going through and computing the summation if you have these simple finite length signals that you're doing. Right, so that's one way that you can do it. This will work only for really those finite length signals. You might be able to apply it if you have one that's infinite length, where maybe you can use it to see a trend, but generally it doesn't work as well if you have either signal is infinite length. If you're not really comfortable with this array method, what you could also do is a graphical method. So your graphical method, this also tends to work a little bit better if you have finite length signals. Helps if you're more of a visual person. So what you want to do is plot your x and your h in terms of k. And like I said before, you could flip-flop. So if there's one that's easier for you to manipulate like this, then maybe you choose that to be the one that you do your shifting and flipping with. So h n minus k, getting that from hk, what you do is you shift n steps to the left, and then flip about the vertical axis. So you will notice that some textbooks, when you're looking at them, when they talk about convolution, they say flip then shift. So the difference there is if you flip first, then you're going to be shifting to the right instead of to the left. So you can do it either way, just something to note if you look at the textbooks, that when they're manipulating signals, they tend to do shift and flip, and then for some reason they say, well, convolution, let's flip then shift. So a little bit of kind of a weird inconsistency there. So then in that case, you would shift right by n after you do the flip. But if we look at what this means, if we're trying to look at this graphically, what you would have is, say you're looking for y of 0. So we know that is a summation. Let's say xk h. If n is 0, then n minus k is just a minus k. And so what you would do is you would sketch out in terms of k. You would have your x of k. So if we're looking at our example that we had, where we just had 3 non-zero values, so you'd have x0, x1, x2, right, so on and so forth. And then you can sketch your h So in this case, since n is 0, we have no shift, it's just a flip. So you'd end up with h0 right? So we're flipping about that vertical axis. And then what you would do is you would take each point k, you would add you would multiply these two and then add it to the next, right? So you'd have k equals 0, or k equals -2. We have 0 times h of 2 is 0, plus at k equals 1, we have 0 times h of 1, plus, and you move along like that. So in this case, our y of 0, the only non-zero multiplication that we have at each of these k's is at k equals 0. So we have an x of 0, h of 0. And you can continue that on. So for, say, y of 1, then you would have the summation of xk, h, 1 minus k. So your x of k is going to stay the same. And now you're going to have your h of 1 minus k. We're going to have it shifted to the right by 1 from what we had in this case here. So this would be your k equals 0, 1, 2, minus 1, minus 2, so on and so forth. And you do the same thing like we did up here, right? So you compare at the same k values, multiply and add to for all of the k's. So in this case, you'd have y of 1, right? So we have 0, 0. This one is non-zero. We have x0 times h1. Non-zero, we're going to add x1, h0, and then we go back to having zeros. Right, so either of these methods will work. It just depends if you're more of a mathematical-minded person and you like using the array method or just brute forcing the summation itself. You can use either of those. If you're more of a visual person, then you can use something like this, actually sketch out both signals, see how those line up, how you would multiply and add each of those individual k's together, right? So both methods will work for whatever it is that you find works best for you. So, like I said, these will work more so if you have finite length signals. If you have maybe one is infinite length, you might be able to massage one of those methods a little bit more easily. But generally, those just work better for finite length signals. However, if you have infinite length, you can always use the convolution sum directly. So let's take an example here, and we'll do some more next time as well. So if you have infinite length signals, then typically we want to use the convolution sum directly. All right, so you might be able to see some patterns. Typically, it's a little bit harder to do that when you have infinite length ones. So let's take, for example, let's say that we had the same h of n that we looked at before. So we have our h of n is a bunch of zeros, 1, 2, 3, right? Same system that we looked at in the last case. But now, instead of our x of n being some finite length signal, let's say instead that is 1/2 to the n u of n. Right, so our u of n we know is equal to 1 for n greater than or equal to 0. Right, so now we have this infinite length x of n. So if I plug this in, y of n is equal to my convolution sum. It's going to be xk h n minus k. So I'll note for me, what I usually find is if you have only one of the signals that has an exponent like this, I typically find it's easier to substitute the k in for that one. Otherwise, you have some additional terms that you have to carry out, kind of break up that this multiplication. So you have an n term and you have a k term. Makes it a little bit messier. But as I said before, you can use either one and you'll still get the same result. So for this one, I'm going to substitute k in here, substitute n minus k in for there. So we get summation. So we're substituting k in here. We have 1/2 to the k, uk, and we have h n minus k. So what we tend to like when we see these types of step signals is we use those to decrease the range on our summation. So if we look at this u of k, we know that u of k is equal to 1 when k is greater than or equal to 0, and 0 otherwise. So we don't need all of those zero sums that we have here. What we can do is we can take this and say, well, actually, I only need to sum from k equals 0 to infinity. And in that range, this u of k is equal to 1. So I can just leave it with this 1/2 k, h, n minus k. Right, so it cleans things up a little bit so we're not carrying around all those extra 0 terms that we don't need. So our h n minus k, what does that look like? Well, our h n minus k is going to be, as we have h of 0 is equal to 1. So when are we going to have this argument is 0? Well, that's going to be when n is equal to k. We know that we have an h of 1 is 2. So when is this going to be equal to 1? That's going to be when k is equal to n minus 1. And the other non-zero term is when we have h of 2. So when is that going to be 2? When k equals n minus 2. All right, so what that means then is that when we're looking at our summation here, we're going to have y of n is equal to, so we have 1/2 to the n, right? Because we have non-zero when k equals n, and when k equals n minus 1. And got my scale factor here, right? H of 1 and h of 2. We have k equals n minus 2. Right? But this is actually missing something very critical. right? So one of the assumptions that we have here, right? So we had this U of k, and U of k is equal to 1 when k is greater than or equal to 0. And so what this means when we do this substitution in here, right, is that if we end up with a k which is less than 0, then we should have had a 0 here. So what that means is that for this term, this is only true when we have n greater than or equal to 0. And this one, when n is greater than or equal to 1, and when n is greater than or equal to 2. Right? Otherwise, what we would have is that our k would be less than 0, and so those terms would actually be canceled out. And so what we actually have is our y of n is going to be 1/2 to the n un, right? So that's going to capture the fact that that n value, or in this case our k, needs to be greater than or equal to 0. For this factor, un minus 1, right? So it's going to capture that same kind of condition, but for this case here, and the same thing for the last case, right? So what these terms are capturing is the fact that x of k is not equal to 0 only if k is greater than or equal to 0, right? Because we had that step signal up here. We need to make sure that we're still accounting for that step in this final solution. All right, so I'll try to do like I did with some of the other topics as well, add some supplemental, going through a couple more examples so you have a chance to see these again. Definitely one of those where it seems a little bit odd at first until you do a couple of the problems and then get more of a feel for what it's actually doing in that operation. So I'll hopefully post those either later tonight or maybe tomorrow.